This video tutorial claimed some location model, scale model and shape parameters. What is the effect of location model in statistics? We can see a graph. The first one, at first let me highlight it. And this is standardized normal, and here the mean for this graph is mu equal to 0. You can see that 0 here. And we will introduce a location parameter for this graph. We should highlight it with blue pen. Unfortunately, no, I made a mistake. We highlight this location model with blue pen, and here the mean mu is 2. So for this distribution we have to add a location parameter mu. Let me say something and write something. Probability of -1. Now we have some function, and you can see that the x is a random variable, and for the range of -1 from 2 for x, the graph is here, the mean mu is 0. And for the same thing, probability of mu -1, we can add a mu for this, for another distribution that is not standardized. Look at this. Look at the gap between the range. Look at the disperse the gap between this range. 2 minus -1 is equal to 3, and for this those two is equal, and for this one we just added mu or a location parameter for another, for this blue one distribution, and for this distribution, find the gap between those two. Mu plus 2 minus mu plus 1. You can see that mu plus no, plus 3. So you can see that the range or the gap between these two distribution is equal. We have some R code, and you will find it in the description box. You can draw some R code for this. And the graph, for one graph the mu is 0, so you can write such thing, or for another graph mu is greater than 2. These two graphs you can write, you can add these two graphs side by side, and this one is the location model for our situation, and this one is standardized. Here mu is equal to 0. And there you can throw some question that what is the effect of location parameter? What is the effect of location parameter? And when the mean mu is equal to 0 and mean mu is equal to 2, what is the difference for those two distribution? This is the effect. You have to say it beautifully. Suppose we have a PDF of our normal distribution, say to sigma root 2 pi. Here sigma is equal to 1, e to the power minus half x minus mu divided by sigma square. Here the mean mu is equal to 0. So and mean mu is equal to 0 and sigma is equal to 1. So the standardized normal PDF will be minus half x square, e to the power minus half x square. Mu is equal to 0, sigma is equal to 1. This is for the standardized form. And the same when we add a location model, and here then it comes mean mu is equal to 2, You can write the PDF function of x e to the power minus half x minus mu sigma square. Uh, for location model, we are not dealing with this sigma parameter, because sigma is a sigma is a scale parameter. For our lesson, sigma is not our concern. We, what is the effect between what is the effect for the location model? This is the standard PDF, and the what is the change for standardized PDF, and what is the change for when we add to in our location model. The change is the change is the change is the effect of location parameter. We write something about location. What is the work of location model? Location just does shifting, you know shifting the distribution. And what is the work of scale? It stretches, stretches or contract the shape of the PDF. There we will introduce the thing threshold. Threshold means minimum, with an example. Uh, we can write the PDF of exponential distribution. Lambda e to the power minus x is greater than 0, and lambda is our parameter. you know and and from this one, how we can draw an exponential location model. Exponential location model. We have to add mean mu for this, and when mean mu is equal to 0, that means it's standardized. Then when mean mu is equal to 0, then we can see that standardized. When we will see it exponential location model, when we will add the mean mu with the x. This is exponential. This is the PDF of exponential distribution, and when we add the mu, then we will call it exponential location model. We will here I will explain an example. Time. Suppose that we have a math problem, and I gave that problem to many students, and some will do that problem by 2 minutes, or some will do by 3 minutes, 4 minutes, 5 minutes. And for those students, what is the minimum value for this problem? Here time is a random variable which cannot be negative, and the minimum value is 2 minutes. And and here 2 is the threshold. threshold or cutoff point. 2 is the threshold parameter or cutoff point, and for time variable it will always be positive. Mu, sometimes for some situation mu is called threshold parameter when mu is the minimum. Assume a situation when we have many random variable x and we know the minimum value of x. We know the minimum value of x. Then for those kind of situation mu is sometimes called threshold parameter. You know, a lot of students make mistakes: location, scale, and shape. But no, but scale is another thing, and shape is another. Shape is not related with location and scale. Shape is totally a different thing. Shape, location, and scale doesn't change the look of a distribution that much. But shape changes the face of something. Changes the changes the whole thing. We will do it by some by we will say something for this. We have some assume that the value for this distribution is sigma is equal to 1, and we have some situation 1.5, sigma is equal to 1 or sigma is equal to 0.5. When the variance is greater, when we have a large variance, the PDF will be extracted, and but the whole area for this one and this one will be 1. So we have to downward the head for this distribution. And when sigma is equal to 0.5, the PDF is contracted, so we have to draw a big tail for sigma is equal to 0.5, and then the tail will be thin. Tail will not be expand.